Okay, so Assalamualaikum and a very good morning. So thank you so much for joining this webinar. Actually, this is series 3 for this year, which is 2023. For this webinar, actually our speaker actually is the one of the petroleum engineering lecturer. All right, so the topic we will cover today, which is the unlocking reservoir potential, the multidisciplinary approach to well stimulation. So a bit about Dr. Mansur is that Associate Professor Dr. Mansur has more than 24 years of experience built upon his technical, operational and management roles in industry and academia. So he has a bachelor degree in geology and a master and PhD in petroleum engineering. So he has been involved in different disciplines, including the project management, flow assurance, piping, environmental engineering, drilling, production engineering, reservoir management, and CCS, which is the carbon capture and storage. So he has lectured on several courses at UTM, Petroleum University of Technology, which is PUT, and also Islamic Azad University, IAU, at Iran. So he is a member of the Society of Petroleum Engineers, which is SPE, is registered as a Chartered Petroleum Engineer at the Energy Institute. So Dr. Mansur also one of the IA subject specialists at the Department of Environment, which is DOE Malaysia. So he has published more than 50 publications in international peer-reviewed journals and conferences, contributed to 5 textbooks, and served on many scientific committees. So currently, Dr. Mansur is an associate professor at UTM and is involved in several consulting projects in petroleum engineering and energy transition. So he is actively involved in multidisciplinary studies, and his current focus is on energy transition. So that's a little bit about Dr. Mansur. So I think Dr. Mansur already ready for this webinar. So the stage is yours. Welcome, Dr. Mansur.
Thank you very much, since we got very far, and I think without further ado, I can share my slide, right? Okay, I think everyone can see the slides. Visible, right?
Yes, yes.
Okay, thank you very much. Assalamu alaikum and good day, everyone. Today we'll discuss the collaborative rules of different disciplines in optimizing well stimulation and how they can actually help maximize the reservoir potential. So for a clear understanding of each slide content, non-expert should read the introductory sentence placed above each sentence. So as you can see here, I've included a sentence here for the non-expert for a clear understanding of the subject. Okay, so this is the agenda. We'll start with an overview of well stimulation, followed by why a multidisciplinary approach is crucial. Then we'll delve into the rules of different disciplines in the process, discuss how we can enhance stimulation effectiveness. We'll also touch upon formation damage, and specifically for scales and precipitates, an approach in solving the problem before diving into some case studies, and we will wrap up with our conclusion. Okay, so well stimulation as its core is a process of course designed to enhance the productivity of oil and gas wells. This process involves various techniques aimed at increasing the connectivity and permeability between the reservoir and the wellbore. And here you can see actually well stimulation techniques, and this can be actually shown for as our reservoir, and this is our wellbore. And the main difference between this well cleaning and oil stimulation is that actually for the cleaning or acid remains near the wellbore, but for well stimulation techniques, acid will actually penetrate deeper into the reservoir, depends on the pressure applied. Okay, let's go for the purpose, but why we do actually need to stimulate wells. The ultimate goal here is to increase the production of hydrocarbon. With time, the natural flow of hydrocarbon may decrease due to the various factors. Well stimulation serves as actually intervention to ramp up the production. So just as education and exercise enhance human development and longevity, well stimulation optimize the productivity and lifespan of hydrocarbon reservoirs. Both processes aim for peak performance over the course of a life of reservoir. As you can see, this is a plot showing the production rate and time, and in each production phase, of course, we need the well stimulation to increase the production. Depends on the presence of the damage. So it's relevant through the entirely hydrocarbon extraction process. So now let's focus on the rule of well stimulation. Maximizing reservoir potential is the key. Think of it as getting the most of actually fluid, getting most out of the fluid juice. You want to squeeze it until the last drop, right? Okay, so similarly, well stimulation also ensures that the maximum possible hydrocarbon are extracted from the reservoir, leading to optimal output and efficiency. On our slide, here you can see that we have a flow chart that depicts various types of stimulation. We have hydraulic fracturing, acid fracturing, and matrix acidizing. And of course, we have a workflow that show actually different process and steps in well stimulation, starting from candidate selection to treatment actually evaluation. And finally, this actually chart shows how stimulation can increase the production, and this is of course really showing the improved performance relationship for a well after and before the stimulation. So the importance of the multidisciplinary approach. Today we're going to tackle multifaceted world of well stimulation. Optimizing well stimulation and maximizing reservoir potential is not a one-man job, or rather a one-discipline job. It requires a collaborative expertise from several fields: flow assurance, geology, geomechanics, chemistry, and other disciplines. All of these fields of expertise play an essential role, much like key components in the complex mechanisms of well stimulation. Flow assurance ensures reliable flow of hydrocarbon. Geology actually provides us with understanding of reservoir and physical and chemical makeups. And then geomechanics actually offers insight into the behavior of rocks under changing physical and environmental stresses. And then we go for the chemistry. Chemistry also is very important, that aids in selecting the best stimulation fluids. Economics also helps in analyzing cost effectiveness and return on investment. And finally, artificial intelligence brings forth advanced algorithms and models to predict, optimize, and control the stimulation process. When these distinct components collaborate, they propel the system towards the best possible well stimulation and the highest potential of the reservoir. In the coming slides, we will explore the unique role each of these disciplines plays, their interplay, and their collective contribution to the goal of well stimulation optimization. Okay, why multidisciplinary approach is a must in optimized well stimulation. The oil and gas industry, specifically the process of well stimulation, is a complex beast, no doubt. There's a multiple of variables, intricate geological consideration, operational nonsenses, economic implication, and let's not forget the evolving technological landscape with artificial intelligence making its mark. That's where our superheroes, flow assurance, geology, geomechanics, chemistry, economics, and artificial intelligence step in. Each discipline offers a unique set of tools and perspective that individually can tackle parts of the problem. But there's an interesting part. These disciplines are not isolated islands. They're more like an archipelago, a group of islands closely scattered in a body of water. The challenges they tackle are interconnected, much like an ecosystem of an archipelago. A solution from one discipline can significantly impact the problem seen by another. So now, when the approach these interconnected challenges with multidisciplinary lens, we are not just creating isolated solutions. Instead, we are actually fostering a collaborative environment that allows for a much more robust, innovative, and optimal solution for well stimulation. So the need for multidisciplinary approach in well stimulation isn't just important. It's absolutely crucial to navigate the complexity and deliver the best results. So this is the rule of artificial intelligence. Artificial intelligence can handle uncertainty. Fuzzy logic, for example, manage vague data suitable for uncertainty management. Linguistic assessment, fuzzy logic. I give you a fuzzy logic because I have a case study I want to show. So fuzzy logic models subjective assessment, flexible for linguistic uncertainties in candidate selection, robustness against incomplete data. Fuzzy logic handles limited data robustly, ensuring reliable screening decision, and handle multidimensional variables. Fuzzy logic actually integrates diverse factors for compressive candidate selection, for example, for hydraulic fracturing, and flexibility and adaptability. Fuzzy logic can adapt to new data, refining the candidate selection process in all stimulation workflow. The rule of flow assurance for deposition and scale management. I just included a sentence here. You can read through and understand the definition of flow assurance. For deposition and scale management, consider high salinity. So I'm going through each one of these items: deposition and scale management, dynamic simulation, equipment compatibility, chemical treatment, and also a case study. So for the first one, flow assurance engineers can mitigate this issue by implementing scale inhibitors that prevents the formation of these scales, thereby ensuring smooth flow of hydrocarbon. Of course, you need to know that in order to access the wellbore, we need to remove this kind of scale. So this is the rule of flow assurance engineer that can do. The next one is the dynamic simulation. Let's take a look at deeper fields with a cold condition. These conditions are conducive to hydrate formation, which can block pipelines and disrupt production. Flow assurance professionals use multi-phase flow simulation tools to forecast hydrate formation and design strategies to prevent it. Equipment compatibility is another area where flow assurance plays a significant role. For example, in sour wells containing high amount of CO2 and H2S, corrosion can be a severe problem. Flow assurance engineers can select corrosion-resistant alloy tubing to resist these corrosive agents to ensure longevity of the well and its equipment. As for chemical treatment, consider wells producing crude oil with high paraffin content. This is much more severe in peninsular fields that have, wax will be precipitated. These wells are prone to wax deposition, which can block the flow of hydrocarbon. Here, flow assurance can help by introducing paraffin inhibitors that significantly reduce the deposition and maintaining the oil flow. Our discussion about flow assurance is enhancing production will be more enlightening with a specific example in the next slides. So this is the rule of geology. So in the contents of well stimulation, geology offers essential contribution beyond general reservoir characterization. Let's focus on this specific aspects such as mineralogy, sedimentology, and also characteristics, natural fracture and fault. So we are going to cover the first three topics. So detailed mineralogical analysis is critical for effective stimulation. For instance, in a sandstone reservoir rich in silicate minerals, a comprehensive mineralogical analysis led to the selection of hydrofluoric acid for stimulation, resulting in an improved flow rate. So clay mineral also can present a significant challenge. These minerals can swell or disperse in response to stimulation treatment, leading to formation damage. So, however, geologists can identify the presence of these minerals and preventive additive can be introduced. One common preventive measure is the use of potassium chloride, KCl, which can stabilize clay minerals and prevent this adverse reaction. Similarly, chloride minerals that contains also iron can react in the presence of strong acids, often used in stimulation treatment, leading to, of course, changes in the permeability. This can impact the effectiveness of stimulation. However, by understanding actually the mineralogy of the reservoir, acid inhibitors can be introduced to control these reactions. So there are others such as natural fracture identification, faults and discontinuities, and also formation damage assessment. So this is very, very important for our case, and there will be a case study that I will present. Role of geomechanics. Geomechanics plays a vital role in optimizing well stimulation. Let's explore some of the key ways geomechanics contributes to this process. Firstly, stress analysis is crucial. Geomechanics help in identifying the in situ stresses, providing valuable insight into the fracture initiations and propagation. These insights can influence the design and execution of stimulation strategies, helping to optimize the results. Next, understanding the mechanical properties of the reservoir rock is very important. Parameters such as Young's modulus and Poisson ratios can aid in predicting how the reservoir will respond to stimulation. For instance, rocks with high Young modulus, they are stiff or brittle, are more likely to fracture, a factor that can leverage in hydraulic fracturing operations. So we have also borehole stability, and I'm going to present a case study published in a journal. Okay, the rule of chemistry, we are going also to discuss the pivotal rule of the chemistry in well stimulation. So firstly, stoichiometry is crucial, it's very critical. It allows us to predict the outcome of the chemical reaction involving well stimulation. By understanding the quantities of reactant needed, we can optimize the process, avoid wastage, and minimize adverse environmental impact. So in this reaction, as you can see, 2 moles of hydrochloric acid react with 1 mole of calcium carbonate. This produces 1 mole of calcium chloride, 1 mole of carbon dioxide, and also 1 molecule of water. So next, let's talk about the kinetics. Okay, so the rate at which chemical reaction occur in well stimulation can greatly impact the efficiency and success of the operation. Fast reaction might lead to premature acid spending, while slow reactions might not deliver the desired stimulation. Therefore, understanding and controlling this kinetic is essential. Just I give you an example. This kinetics is very important for designing the stimulation process in sandstone and carbonate. You might know that this rocks can address or react to the acid with different actually reaction rates. So the kinetic As you can see here, for this reaction might took something like this. We have the rate, we have the K, which is the rate constant, and we have the HCl, which is the concentration of hydrochloric acid. And then we have the concentration of calcium carbonate. So understanding the chemical for this reaction, operators can control the rate at which rock is dissolved. So, for example, if the reaction is too fast, it might lead to the creation of large wormholes that can reduce the overall effectiveness of the acidizing process. On the other hand, if the reaction is too slow, like sandstone rocks, it might not provide the desired increase in permeability. Therefore, operators might adjust the acid concentration, temperature, and other factors to achieve the optimal reaction rate. Okay, so hence understanding reaction kinetic is essential for optimizing of well stimulation process. Okay, so acid selection is the right is also dependent on the stoichiometry and also the kinetic, choosing the right acid for stimulation. Of course, this is completely related to the geology of the reservoir. Okay, so different acid reacts differently with reservoir rock. For instance, hydrochloric acid is commonly used for limestone and dolomite formations, while hydrofluoric acid is used for sandstone. So the choice of acid can affect the reaction rate, the extent of rock dissolution, and also the potential of formation damage. Finally, we must consider the environmental consideration or implications. Many of the chemicals used in well stimulation, including acids, can pose significant environmental risk. Careful selection and handling of these chemicals, guided by our understanding of the chemistry, can help mitigate actually these risks. So this is an example. Actually, you can actually access this YouTube video by going through this link here. In this example, actually, with the help of stoichiometry and kinetics, we can, and of course, there are some information that needed. We need to know the volume of formation, and then we need to know the amount of calcite that present. For example, here, the amount of calcite is 10% of the sandstone rock. And then we need to know the chemical reaction between the HCl and calcite in order to come up with the stoichiometry and calculate the amount of acid. And then we need to come up with the percentage of the acid, and then of course we need a conversion factor. So you can actually access the full video about the stoichiometry and kinetic from this YouTube video. Actually is designed by me. Okay, so the rule of economics. In this segment of our discussion, we are going to actually shift our focus to the rule of economics in well stimulation. First on our list is the cost-benefit analysis. Well stimulation is an investment, of course, and all investment, it involves cost and potential benefits. The cost includes actually the direct expense of the stimulation process, such as cost of chemical, equipment, and labor. The benefits are the increased production of oil and gas results from the stimulation. A detailed economic analysis can help determine whether the potential increase in production justifies the cost of a stimulation. For example, a company might estimate that a hydraulic fracturing operation will cost $1 million, but it could potentially increase the production by additional 50,000 barrels of oil. So if the market price of oil is $70 per barrel, the increased production could result in additional revenue of $3.5 million. So after subtracting the cost of the operation, the net benefit would be 2.5 million. So this is simplified example, but it illustrates the kind of calculation involved in cost benefit actually analysis. So next, we have risk assessment. Well stimulation, particularly techniques like hydraulic fracturing and acidizing, involve risks. So this includes the risk of well failure, the risk of environmental contamination, and others, like the BP well in Macondo wells. So this risk can have economic impacts, such as the cost of cleanup efforts or potential legal liabilities. An economic analysis can help quantify these risks and factor them into decision-making process. So for instance, a company might estimate that there is a 1% chance of well failure that would result in 10 million in cleanup cost and lost production. So the expected cost of this risk then would be about $100,000. So this expected cost can be included in the economic analysis of the well stimulation operation. I'm going to skip this two, and because of the time, okay, formation damage. So formation damage refers to the change in the area of formation near the wellbore, so the wellbore region. So this is the definition of the formation damage. So of course, understanding and addressing formation damage is important in well stimulation for several reasons. Maximizing the production well stimulation techniques like hydraulic fracturing and acidizing aims to increase the permeability of the reservoir and also optimize stimulation strategies and maximize or minimize the future damage and predictive analysis. Here in this chart, we have actually classified, or the formation damage is classified to mechanical damage and chemical mechanisms. And then we are going to focus on the solids, which are precipitates and scale in the later slides, and we are going to actually dig into this kind of solids. So type of depositions, this is a list of potential source of formation damage in oil wells. So organic materials like wax and asphalting can originate from crude oil itself. Inorganic materials such as various types of scales can come from water, and then sand, silt, and clay can present in the formation rock, and also corrosion products can come from the tubing or casing. And bacterial debris also can result from bacteria present in the well. As you can see here, this is our well, and this is our well, and then as you can see, the majority of the pressure or the resistance is here, the near of wellbore. And then we have classified this arbitrary actually classification. The majority of the total, the majority of resistance is around the wellbore, which well stimulation takes place, and this is the aim of well stimulation, actually, to remove this kind of damage. About 5 to 15% of the total resistance is happening into our tubing and surface facilities. Okay. So this is an example. This is a slide depicting the asphaltenes. What are the characteristics of asphaltene? Actually, asphaltene is in oil precipitates due to the change in pressure or temperature. So the precipitates can cause plugging, impacting oil production significantly. So detecting involves measuring asphaltene onset pressure and concentration. So AOP and AOC actually. And then chemical inhibitors can prevent precipitation even beyond asphaltene actually onset concentration limits. So managing operation conditions below AOC can reduce asphaltene related issues. For the detection part, as you can see, this classification is for when we have actually the size of micro asphaltene is 3 nanometer to actually 1 micrometer. We actually cannot detect it by or the measurement cannot done by this kind of AOP or AOC, but the detection can be done by commercial actually NIR, which is the near infrared and high pressure microscopy to identify the asphaltene flocculation and also We can use particle size analysis techniques, and there are also other references. For example, asphaltene stability trend from this reference can use in order to detect asphaltene. And also we have standard ASTM D4124 is used also for to stabilize for separation of asphaltene into 4 fractions. It's let's say SARA analysis, which stands for saturates, aromatics, resin, and asphaltene fractions. Okay, so this is wax. The characteristics of wax is included here, and as you can see, wax on oil precipitates when temperature drops below wax appearance temperature. So it can, of course, potentially plug the pipeline and reducing the oil flow rate. Wax deposition is critical problem in offshore and Arctic condition. Wax inhibitor, heat insulators, mechanical methods also can be used to manage wax problem. And normally we use, pigging or hot oiling in order to mitigate this wax. There is a case study, and I'm going to present it for you about this. And of course, there are standards, and there are actually ways of detecting this asphaltene, and the majority of them are actually using, for WAT stands for wax appearance temperature, and also wax disappearance temperature is very important here. These are 2 important parameters when we dealing with wax in crude oil. When the temperature at which wax begins to crystallize and precipitates out of the solution, this is WAT. As the temperature of the oil drops below its this point, which is WAT, usually when being transported from the hot subsurface condition to the cooler surface, or actually subsea, the wax begins to solidify and can start causing issues like clogging pipelines. So wax disappearance temperature, this is the temperature at which the solid wax in the oil begins to dissolve back into the oil. So when the temperature of the oil rises above the WDT, the wax start to melt and flow again with the oil. It's typically higher than WAT because of hysteresis, a phenomenon where the dissolution process requires more energy than the crystallization process. So here it's important to know these parameters to design appropriate strategies to manage wax problem in oil production. For example, heating the oil to a temperature above WDT can help to manage wax. And of course, for the detection, we can use differential scanning colorimetry. We can use SARA test. We can use ASTM D2500, IP219, a test that actually from the Energy Institute. It's all about the pour point of, and then ASTM D3117. This is standard for determining wax appearance point of distillate fuels. And also we have ASTM D5773 or IP446 standard test to determine cloud point of petroleum product and liquid fuel using an automated instruments. So this is naphthenate, and this is of course, naphthenate and emulsion. The characteristics, naphthenates are complex organic compounds present in crude oil, specifically in an acidic actually component of oil. They can cause operational problems in oil and gas. And also the detection, we can use total acid number, and then water analysis. We can use emulsion characteristics for the emulsion, of course. And then factors that affecting emulsion are the density, viscosity, and also saturates the amount of asphaltene, resin, and fine solids. This can actually affect the emulsion. This is inorganic scale Inorganic scale are mineral deposits such as barium, strontium, calcium compounds. Scales can form when incompatible water mix in the reservoir or production equipment. Scales can be detected through production decline, inspection, and fluid analysis. We can remove the scales using acid treatment or mechanical methods. And of course, there are also prevention. We can use scale inhibitors to prevent actually these scales. How we can detect it? Of course, water analysis is very important. XRD to know the component of this, and also we have nature of the deposits, whether it's calcium carbonates or whether it's barium sulfate, and of course all of you know that the pH is very important, but the pH is directly related, and it's important for the first one, which is calcium carbonate, but for barium sulfate, because of the barium sulfate is not actually solvable, dissolving in water, it's not important. So that analysis and the scaling index also will be used. Not to forget, simulation also is very important, using ScaleCam and other packages. So what are the approach actually to solve the problem? So we have reservoir and production data analysis. We have laboratory data. We can do history matching, and we can actually go for parametric study and design of experiment. The purpose is from all of this approach is to understand the problem, to know, for example, whether this organic or inorganic, what is the type of formation damage? Is it from fine? Is it from emulsion? Is it from, so this kind of diagnostics needs to be done in order to know actually the problem, and then devise and then come up with a solution appropriate for that problem. And of course, we need to conduct economic analysis in order to know the benefits of conducting this actually operation. And of course, these kind of techniques can be used intrusive and non-intrusive. When we say non-intrusive, it's all about laboratory analysis actually, and then fluid analysis, temperature and pressure logging, and also chemical treatment and reservoir simulation and design of experiment. This is all non-intrusive. And of course, for this intrusive one, we have scale removal, reperforation, and also acid treatment. Okay, so this is the laboratory analysis. Actually, our team can do this kind of, normally when we do this kind of actually test, whether it's crude oil or it's water, we need to actually conduct this kind of experiment for the crude oil, and then we conduct, of course, this experiment for the water, and then we need to access the deposit. We need to access, for example, is if we have any scale or any type. So we need to know, for example, what is the depth that this deposit is retrieved from, whether it's organic or inorganic. If it's inorganic, we need to conduct this kind of test. If it's organic, of course, we need to go for this kind of test. And then we need to do a compatibility test with formulation. And then based on this compatibility test, we will propose the chemical formulation for this type of actually problems. Okay. So these are the laboratory analysis that will be conducted based on this standard. Of course, for the modified SARA, we will include this kind of naphthenate and microcrystalline wax, and we have CII, which is the actually colloidal instability index. Based on that, we can say that if the CII is more than 0.9, it says that it's actually showing we have instability. And then if it's less than 0.5, it shows that the crude are general in actually in a stable state. Okay, so this kind of analysis also will be conducted in the laboratory in order to come up with the final formulation to treat the well. And this is an example that is for VAX issue. And of course, we have a deposit, and we need to test this kind of deposit with various formulation. For example, if this normally this kind of xylene will be used in order to dissolve this kind of wax and asphaltene, but all of you know that this xylene is very carcinogenic, and also there are strict regulation in using this kind of chemical in well stimulation. Okay, so this is actually an illustration of how actually a chemical treatment will be utilized and then this is different steps that normally we use. We prepare the chemical, and then we mobilize this to the platform, and then we rig up the chemical and equipment. We do the chemical treatment, and then we demobilize our and as you can see, normal chemical treatment, it's mixed with well stimulation. We have several steps, and this is the treatment that is specifically designed for to remove or to stabilize the fine within the reservoir. As you can see, we need to do tubing pickling, and then we do pre-flush, and then we do acidizing treatment. We post-flush, and then flow back, and then another pre-flush. We go for fine stabilizer, and we go for post-flush. We soak it for 12 or 24 hours, and then we will flow back. And this is showing actually the type of casing and cement, and also the well is actually sand screen perforation. And so this is a general illustration of how this kind of process is used. Okay, and then this is just a demonstration of a technology for those who are not expert in this field. Just I want to show you how this fine stabilizer will be actually working in subsurface. Just consider a subsurface strata, and then from this subsurface, we just take a small sample of the pores, and then all of you know that this porosity, this is actually the porosity, and then the pore space in subsurface, and then normally actually the fine is originated from these rocks, and then will migrate through this kind of pores and reach to our well. So in this case, I'm going to illustrate how fine stabilizer that shows shown in the previous slide will work. So this is actually our well, and this is the well is located here, and then here is our pores. An example of this actually. In this case, as you can see, normal production fines is produced into the wellbore. Okay. So when we inject the fine stabilizer will be injected into the pore space. It will be soaked for 12 or 24 hours. After that, it will flow back, and then all of the fines will be actually flocculated and coagulated. And then after that, we are having a flow that free of actually fines. And just for your understanding, this technology is taken from well treatment, from water treatment. So we adopt this kind of technology from water treatment to environmental engineering to subsurface, and widely actually used in well stimulation. So normally, actually for the coagulant part, it has a positive charges, and these positive charges will react with the negative charges of the surface of the fine plane. And then we have flocculant, which is a long chain flocculant compound, will agglomerate the microfine. Okay. So fine stabilizer reduce the fine bridging in the formation pore floats, improve the critical drawdown. Of course, for you to understand this critical drawdown, higher actually critical drawdown means that after increasing of the drawdown, sand will be produced or fine will be produced. So that's why we are not going to impose much more drawdown to our well, because of the danger of producing sand into the formation and also reduce formation damage. So this is a status of actually problems, and then the remedial action and the prevention action, and also the maturity of the application. And as you can see here, for the asphaltene and wax, we can do actually the remedial is a macroemulsion and dissolver. And I'm going to show you an example for this. For waxes and paraffin deposition, there are actually thermal and chemical treatment. And of course, for the preventive, we have inhibitors. And others, as you can see in these tables, are showing the prevention and remedial action and the state of each of these technologies in the market. And then this is a case study number 1, published in Neural Computing and Application, using artificial intelligence, specifically fuzzy logic, in order to screen the well. For this problem, this study aims to optimize the net present value, or this is economic analysis of carbonate well stimulation for hydraulic fracturing treatment. So NPV, or net present value, is an economic measure that uses to decide whether to fracture certain wells. So well number 16, as you can see here, well number 16, formation of permeability of 9 millidarcy, net height of 75 meters. Sharing reservoir pressure is about 4,552 psi. Approximately 800 oil is produced from this well. This is demonstrated an excellent results. Its incremental revenue significantly exceed cost across all ranges, making it an excellent candidate for hydraulic fracturing. So the optimal fracture length correspond to the maximum NPV. So we have other wells such as well number 54 and also well number 23. As you can see, it shows actually exclusively negative NPV values. So suggesting the incremental revenue wouldn't justify the cost, making it an unsuitable candidate for fracturing. So this could occur in wells with high permeability, high skin, high water cut, or low reservoir pressure. Overall, the proposed model effectively optimized hydraulic fracturing candidate for selection performance, specifically under condition of high uncertainty. Future work should address the issue of fracture design, which wasn't included in this study. So this is also showing how type 2 fuzzy logic can handle uncertainty. So this 3D surface plots show that demonstrate the ranking candidate well for hydraulic fracturing. Of course, we use type 1 fuzzy logic and type 2 fuzzy logic. And then, as you can see, type 1 fuzzy logic is more sensitive to small changes, as you can see here in this case, to small changes, leading to large output changes. Conversely, type 2 fuzzy logic plot shows a smoother transition, making it handles input uncertainties better than it's in less prone to drastic change in output for minor input variations. So type 2 fuzzy logic proves to be more a reliable tool for well evaluation in the presence of higher uncertainties. So case study 2 is also published in Journal of Petroleum Science and Engineering. This is an integral approach in determining rock properties from well logs in heterogeneous carbonate rock. So what was the problem in this case? We were facing a challenge of developing a field for potential stimulation activities. So where continuous log data isn't available for all wells, we haven't had for all wells, there was a lack of well logs. So limiting our understanding of the field characteristics. So critical to this development is the acquisition of rock elastic properties or log elastic data for constructing accurate stress profile and determining Young modulus and Poisson ratio. So our task, therefore, is to devise a strategy to employ techniques that enable us to accurately infer or extrapolate the necessary geological and rock properties, ensuring a reliable basis for assessing the field suitability for stimulation. As you can see, we use three methods in developing or coming up with actually VP or compressional shear data. After that, we validate the results with leak-off test data and lab or UCS data, and then we compare the results, and then VP were validated by one bell lock, and then after that we come up with the VS or shear data based on the VP data, and then we actually based on the current correlations, we determine the Poisson ratio, shear modulus, and Young modulus, and then of course these are dynamic data. We need to turn them to static Young modulus, and then finally rock elastic properties achieved, and then we've been able to come up with stress profiling and then design of actually experiments. The third one is experimental characteristics of a new high strength ultra lightweight composite propan derived from renewable resources. So this is also we have a patent for that, but the good thing is that this is an a multidisciplinary approach also, material science, numerical analysis, strengths analysis, and also using renewable resources was one of the actually advantage of this work. To give you a perspective of what is going on, so in hydraulic fracturing, normally propant is very important, such as hydraulic fracturing fluid. So fracturing fluid normally will be injected into the well at high pumping rate, which causes fracture to form in the formation here. So in order to prevent this fracture to close, we need to pump certain materials that can actually prevent closure of this fracture. That's why we call it propant. So propant needs to be injected down there in order to prevent closure of these fractures and actually provide a pathway for the fluid to migrate or to flow from the reservoir to the wellbore. Okay, so in this project, we developed actually a propant for hydraulic fracturing with deformable substrates and high compressive strengths. It was excellent, of course. It has low specific gravity, high crush resistance, and also better fracture conductivity. We did characterization like as FSM, SCM, XRD, TGA, and also not to forget, also we have consulted actually several people about polymerization, about actually surface modification, and about other material properties. And at the end, as you can see, this is the fracture conductivity is performed, and it shows that this product outperforms the comparative comparative product in the market, which is ultra lightweight 1.2 from Baker Hughes, and it shows higher actually pressure or higher. It can withstand until 6,000 psi in the subsurface. Okay, so case study 4. Also, this one is well A is a dual string producer well. The well was shut in, and then low production, and then also suspect completion skin, and then reduced PI due to the attraction of colloidal, mobile, and deposit. So this was due to the drilling fluid used due to the drilling plugging, and then there was no breaker that pump to dissolve this drilling fluid. So also there was some tracers of naphthanates that recovered during the intervention job. So the deposit sample, as you can see, was black in color and looked like tar ball. So no sharp melting point at 98 degrees centigrade. So this is showing that, of course, the absence of sharp melting point could provide useful clues about the nature of composition of the substance. It could suggest the deposit is a mixture of different compounds, or that is has a complex molecular structure. This might influence how the deposit can be handled or treated in a well stimulation or intervention job. So we've conduct a preliminary dissolution test conducted that shows minor dissolution of low molecular weight organic. Okay, and then this is the results of loss of ignition, and then other tests conducted for this actually analysis. We conduct XRD and other tests also conducted in order to see or to know what are the composition of and then we conduct XRD and saturates. It's composed of macrocrystalline wax and microcrystalline wax, also conducted. SARA test and also modified SARA test is conducted, and then the output of this test actually helps the team to come up with a good formulation for that actually. So based on that, a custom-made chemical formulation is made for this chemical, and then control of reaction, of course, is very important. I think the time is going up, and then this is the results, and this is the case study. Of course, there is a formulation design approach for surfactant, and then the value creation, the result of this case study. And this is about the dynamic simulation conducted via Olga. And then, of course, this is the services that we can do about intelligent data mining, dynamic simulation, innovative treatments. Our team available to do that for you. And then we have expert consultancy. And then, of course, there will be some training courses about this. For the conclusion, the multidisciplinary approach is essential for addressing reservoir management challenges, necessitating the combined insights and expertise of various professionals in the oil and gas industry. So the solution to the challenges are only able to be developed with appropriate diagnostic, prognosis, and inference. Prevention is better, of course, than cure. Integration knowledge from subsurface to the surface enables a comprehensive understanding that encompasses various aspects such as reservoir properties, lithology, chemistry, flow assurance, geomechanics, AI, and so forth. So the future of well stimulation is innovative through collaboration. Thank you very much. And this is the references used, and open floor for question and discussion.
Okay, thank you so much, Dr. Mansour. Very fruitful presentation. All right. So for the audience, if you have any questions, maybe you can write down in the comments box. All right, and then we will read it out.
Yeah, I think if there is no question, or if the question is more actually complicated, they can write email or ask me question, whatever time is allocated for them.
Yeah, sure. So for the audience, if you have any questions or if you have any info to share with Dr. Mansour, because Dr. Mansour also doing the consultation project, all right, for this topic, right? So maybe if you are interested, maybe you can contact Dr. Mansour lah via email, all right? Okay, Dr. Mansour?
Okay.
All right, so thank you so much. All right, Dr. Mansour, for this, I think very good info lah. All right, this is very what we call it, very hot topics for today. All right, so thank you so much for joining. But before that, all right, Dr. Mansour, maybe you can share the slide again, because we have.
Okay. Your slide.
Yeah, at the end of your slide.
Which slide?
For last slide. I think for last slide. For last slide.
Conclusion?
No. Or can I share my slide?
Yeah.
Okay, thank you. Wait, Okay, so for the audience, all right, so we will have, all right, some upcoming event, all right, for next month now, which is August, all right. So one of it is the upcoming webinar, which is webinar series 4 for year 2023. The topic is what is the rheology for oil and gas application. So the speaker actually is delivered by the Associate Professor Dr. Agus Arshad, and the moderator is Dr. Azad lah. Right. So if you have a free time, maybe you can join again our next webinar lah. All right. And then we also have some professional training and short courses offered by IFOG. All right. So this is the list, all right, for the training. All right. Okay, and you can see here, we also list down the dates, all right, and the venue of the course lah. So if you are interested for any courses, all right, you can contact us lah, all right, to register and so on. We will give you the poster and so on. All right, and next. All right, so this is the contact, all right, if you are interested with any courses that we are offered. All right, so maybe you can contact the one of the PIC, all right, IFOG, if you are interested for any courses lah. All right, so I think that's all for today's webinar. Thank you so much for spending your time, all right, to join our webinar. All right, and hopefully, all right, we will see you again in the next webinar and any courses, all right. And again, thank you so much, Dr. Manso, for your sharing. All right, and Assalamualaikum.
Wa alaikum assalam.